Right, so we are picking up where we left off. Well, that's interesting. This has gone, turned itself off again. Well, hopefully there's something recording sound. Pick up where we left off when we were talking about our quadratic functions and then parabolas, x in the form of x equals y squared turned on its side. And we had a little introduction to relations and functions back then. So I'm just going to reinforce what I talked about then. If you missed that lesson, that's okay. If you haven't watched the video yet, you'll get a reinforcing of that now. And then we'll go on and look more specifically at domain and range, which are going to be important concepts, and they will definitely come up on the exam. So we kind of want to know them. A reminder of what a relation is. A relation is a set of points in a plane, or a set of ordered pairs. Numbers that go together in a pair, and there's an order. The first one we usually think of with a relation as an input value. The second one, the value that comes out of the thing, out of the relation, an output value. You get a present. So we had a little look at relations and functions, and we talked about functions are special relations. They're the special ones where the first element in an ordered pair can only ever go on to, at most, one other value. So I'm going to skip down a little bit. You can see the definition there. A function is a relation in which no two different ordered pairs have the same x-coordinate or same first element. It means if you put a number into a function, it always gives the same answer. If you put in 3 into y equals x squared, we always get 9. If I put 7 into 2x minus 5. I always get whatever that is, 9 or something. 14 minus 5, yeah, check it for me, boys. That's it, I can see. Dyer's nearly there. Yeah, okay, you got there. That's on recording. So, we have a little test, and we talked about the little test that makes it easy to see whether or not a relation is a function. And it was the vertical line test. Remember, the equation of a vertical line, x equals a number. Because everywhere on that vertical line I've got the same x-coordinate. If ever a vertical line touches a graph of a relation in more than one place, that means that x-coordinate is being mapped onto two different y-coordinates. It's not a function. Still a relation, still a set of ordered pairs, but not a function. So you can see here for the very first example we've got on the left there, this one's a function. That's not a problem because wherever I draw a vertical line, and you can see they've conveniently drawn a lot of vertical lines with the grid there, it is never going to cross the relation more than once. So that's fine. That is a function. This example here, we've got our x equals y squared, and we already looked at why that's not a function. Because if I put in x equals 4, I could have y equaling 2 or y equaling negative 2. Two different answers for the one input, not a function. We showed you the old school sort of mapping, where they map from one set to another. Here is remember the set of first elements we call the domain. And I mentioned that last time. I don't know if I mentioned the output. It has its own special name too. That's called the range. So the set of all the possible second elements, the outputs, they're the range. So we go from a domain, from a set of values we can put into the function, to a range, a set of output values. This one here, because 3 maps onto either -1 or 5 when I follow along the arrows, that's no good. That is not a function. It's a relation, it's a rule, it's a set of ordered pairs. If I wanted to write that mapping as a set of ordered pairs, I could write it as 3, -1, 3, 5, and 4, 5. Can you see how those ordered pairs correspond to the diagram, to the picture? It's fairly straightforward. That's good. Sometimes we could just have a description, the set of all points in the first quadrant. So there they've got a diagram of it. Obviously not a function because for all of those x values, or every positive x value, there's an infinite number of y values. No good. Not a function, is a relation. And again, we could just have scattered points or a random list of ordered pairs. They've called it a finite set of points. That's another way of saying a list of ordered pairs. Okay, so there are all the different ways we can do it. As long as each first element maps onto, at most, one other element, we're fine. We're good. The algebraic test is just going to tell you that if you substitute it in, there's only one possible answer. We've looked at that already. And the vertical line test we've looked at as well. So, there's a few questions there for you. What have we got, 11? Determine which of those equations or graphs represent functions and which are just relations. We'll give you like 3 or 4 minutes, have a chat with your friends, and then we'll pick up where we left off. If you think you need to ask a question, you can do that also. Nice style. Here, so we've got questions here. Use algebraic methods to decide whether or not these relations are functions. Explain your answer. Y equals x squared minus 9. Is that a function? Oh, I saw a tiny nod of the head there. Tried to disguise it, Georgia, but it was busted. It's correct, isn't it? Of course it's a function. What's that a representation of? What is that equation? It's a parabola. We know a parabola is symmetrical. We know that for every x value, there's only one possible y value, isn't it? If I take a number and square it and subtract 9, does the answer ever change? No. Whatever number I put in, I'm always going to get the same answer. Great, that's a function. X plus y equals 9. What sort of relation is that? If you wanted to describe it, what would you call it? Straight line, linear equation, yeah, anything like that. When I put in a number for x, there's only going to be one possible value for y. Terrific. That's going to be a function. My next one, x squared plus y squared equals 9. What does that look like if I try to draw it on my... Yeah, what do you reckon, Brett? Circle, isn't it? Circle. Is the vertical line going to cut my circle in more than one place? I think it will. If x equals 0, y could equal 3 or negative 3. That's a relation, but not a function. Vertical line tests. All right, you're just going to call them out in unison, see if you can get yourselves in sync. You're either going to tell me relation or function. What's the first one? Next one. Next one. Next one. We're doing well. Next one. Next one. Next one. Next one. Relation, lovely people. Good job. Why isn't it a function? Because at this one value only, there are 2 possible values for that x value. It was a function everywhere else because it had open circles. One open, if I zoom in a bit, you might be able to see them more clearly. Open circle, this bit here, that's okay. This bit here, that's okay. This bit here where they're both coloured in at the one point, that ruined it for everyone. I hate it when one person comes along and ruins the whole fun for everyone. That one point did it. I like the way everyone's now looking around the room accusingly at one of their friends. It's good. That's exactly how it is. That's how the world works. Wow, there you go. There's the example of y squared equals x turned on its side. I just made a note there that although we could rotate it by 90 degrees, it's also a reflection in the line y equals x, which implies that it's an inverse function. We haven't got to that yet, but we will eventually get to that. Or inverse of the function. It may or may not be a function, the inverse, and we've got a way for testing that as well. And we talked about how if we just took the positive root or the negative root, that's okay. Individually, that yellow bit that I've highlighted there, y equals root x, that's a function on its own. The blue bit highlighted, y equals negative root x, that's a function. It's just when we put them together and we have y squared equals x, we're in trouble, not a function. Guess what? Some easy bits. Function notation, just to make sure we're all comfortable with what we're talking about. We've seen the bit down the bottom, f of x equals 2x plus 3. Sometimes you will see some old-fashioned writing, f such that x is mapped onto the point 2x plus 3. That's another way of writing the same thing, f of x equals 2x plus 3. It's important that you're aware that that's a different way of writing it because we don't write your external exam. So we want you to be familiar with both. Almost always we're going to use f of x equals, and probably in the exam that's what they'll use. But when you're doing some, revision online and you might go on a Khan Academy or somewhere else, they might show that notation, so it's important you've at least seen it. This is just reminding us is mapped onto, they say is converted to, mapped onto is probably more common. They talk about it being a mapping. That's when we're thinking about every relation is a set of ordered pairs. It's a point on a Cartesian plane, which you might call a mapping. few little simple substitution questions here. We might just do the ACE ones, A, C, E for each of these. All you have to do when you're doing these is take the value inside the brackets and substitute it for the variable. Do you need to see an example, or are we 100% confident we could do it? I'll do C, 1C. F of -1 is going to be 3 times -1 plus 2. -3 plus 2 is -1. I worked up the page because I don't have room. You, of course, will work down the page and make it all beautiful in your books. There are 9 to do. That should take us 1 minute. Go for it. Did that pause it on the screen? Yeah.
All you're doing is swapping the x for the value in the bracket. And solving the value.
Unpause the wrong screen. How do we go? Did I get them right, or did I make a mistake somewhere? Sometimes I make mistakes. Check it. Make sure we agree. A non-horizontal vehicle on your page. Right there. Your previous teacher said you would be that. Yeah, back when she was Miss Appleton, she was like, Paul wouldn't have liked it. I would hate it.
But they do the hours.
Because how do I know what it is?
It's 17.
Or is it 1 7/4? How do I know? Yeah. Oh, don't write. I don't want to see this. Some people, I'm not naming any names, am I, Nick? So that's all right. Don't write something like that. That's going to make me cry, isn't it? How do I know whether that's 17/4 or 1 7/4 or... Oh, right here. Oh, doesn't it? Did anyone else just get a little bit of vomit in their mouth when they saw it? Yeah, I thought so. Don't do that. Keep me happy. How did I go? Did I get my maths right? Was I okay? It's okay if I made a mistake. Just tell me so I sort it out. But are we okay with the procedure? Take the number, substitute it in. Don't forget about your positives and negatives. Make sure you get them right. Most common mistake when people get to -3 and they square it, they forget to make a +3, but then it had a negative in front of the bracket. So it was still 3 times -3, -9. Minus -3 squared is +9, but I've got to subtract it. So -18 plus 2 got me the -16. That's the one that sometimes upsets a few people. a couple more to try. It's good to be able to substitute in slightly more unusual things than just a number. So just the highlighted ones there, and maybe the one which I put a box around. I don't know why I put a box around it when I highlighted all the others, but change. Variety is good, right? Yeah. All right, have a go at those. Again, we're here if you need a hand, if you've got a question. You need me to zoom in a bit, Liam. Is that big enough to read? Or is that, if that's still not big enough to read, you need glasses more than I do. How do you sub in A? You replace X with A. 7 take 3A. Yeah. It's just getting you comfortable that sometimes we'll substitute in other variables into equations. So yeah, it's a little off-putting at first, but it's easy, isn't it? It's actually easier than substituting in a number because you can't mess it up. Yeah. Hand in the air like you just don't care. That little arrow means X is mapped on the point that X in and get that out. Another way of saying it. Well, because there's different ways of saying the same thing. I'm getting you comfortable with the fact that there are.
Can I help anyone?
You're comfortable with your way of saying the same thing. Really? You only have one name that you like. That's not how I would do But they're all different ways of describing the same thing. What do you call yourself? Another way of saying the same thing. Oh, I didn't even pause it. That's going to be a boring part of the video. Look, substitute A. I replace the X with A. It's not giving me my pen. Give me my pen back, please. What colour are we going with? Let's change it up. Oh, that one looks nice, yeah. I was feeling pink too. How interesting. 7 take 3A equals 7 minus 3 times negative A. You're going to simplify that to 7 plus 3A. 7 subtract X minus 2. 9 take X. Oh, what have I done? Minus 3X. Ah. Let's try that again. 7 minus 3 times X plus 2. Helps if I read the question. 7 minus 6 will be 1. Take 3X. F of X squared. Oh, why was I so cruel to you? 2 times X squared squared plus 3 times X squared minus 1. 2x to the power of 4 plus 3x squared, take 1. F of negative x. 2 by negative x, when I square it, that negative is going to disappear, isn't it? Plus 3 times negative x, take 1. 2x squared, take 3x, take 1. Lucky last.
Give yourself a pretty little star and a well done me if you get them all right.
There you go. 2x plus h all squared plus 3x plus h minus 1. You could leave it like that, or you could expand it. If you expand it, please don't get it wrong.
You're going to need to be able to do this for later in the course this year.
It's not random that they put x plus h in there. You will see it later on, as Miss Kinnear just said. So keep that in mind. 2x squared plus 4xh plus 2h squared plus 3x plus 3h, take 1. Lucky last, 2 times f of x take 1 plus 5, and I've got f of x is x squared, so this is going to be 2 x take 1 squared, so f of x take 1 is the x take 1 all squared, and then I've got to add 5 on the end. If we're going to expand that, none of you are confused anymore by the 2x in the middle or the 2xh in the previous question, which is great. If you are, you better wave at Miss Kinnear subtly now, but you'll probably realise what's going on as soon as she starts speaking, and you'll go, oh yeah, that's right.
Anybody need any help with any of those?
Happy enough? If Ed's happy, we're all happy. That's good. All right, last little bit. Domain and range. Domain, the numbers I can put in. Range, numbers I get out. Common questions will be to give you an equation or to give you a diagram, a graph, and ask you to state the domain and the range. The set of values that I can put in, the set of values I can get out. The first little bit about showing the domain or range in different notation doesn't really matter to me. What I'm really interested, and in the textbook they talk about this being implied domain. Usually, with most mathematical functions, we can substitute in any number and we can get an answer out of it. But there are some things we cannot do in the real number system. We can define different number systems where we're going to pretend we can do those things, but there are some things that we can't do in the real number system. So you need to be on the lookout for these when you see an equation. These are the things you're looking out for as a clue. I've got to be careful when they're asking me about the domain. We'll look at a couple of examples, but I just want to get these things in our head first. First of all, an even-powered root of a negative number. Square root of -4. Is there a real number answer to the square root of -4? No, because I can't have a positive number, square it and end up with a negative. I can't have a negative number. When I square it, I'm going to end up with a positive. So I can't ever equal -4. So even-powered roots, it's a problem. 4th root, 6th root of an even number, of a negative number, doesn't work. An even-powered root of a negative number doesn't work. We've got to look at making sure that the value under the radical sign is greater than or equal to 0. So an example of that, if I just had something like f of x equals the square root of 2x take 3. And I wanted to find the domain of that function. I look at it and I go, oh, square root, that's one of the things which I'm not allowed to do. What am I not allowed to do? Not allowed to square root a negative. So for the domain, I would know that 2x minus 3 must be greater than or equal to 0. The bit under the square root sign has to be greater than or equal to 0. What do I do from there? Obviously, that's not a nice way of writing the domain, is it? So I just rearrange it and get what x is. This would be the same as 2x has to be greater than or equal to 3. Oh, x has to be greater than or equal to 3 over 2, with a nice horizontal vinculum there for Nick, which is good. Do we understand what I was doing there? If I took a number that was less than 1.5 and I substituted it in, I'd have a negative number under the square root sign, and we know that doesn't work nicely. Another thing we can't do in maths, divide by 0. Division by 0 is undefined. We are unable to do that. So if I have an x in a denominator anywhere, I'm always thinking this isn't going to be defined for all values. We've seen this before when we find vertical asymptotes, haven't we? Remember when we find our vertical asymptotes for our hyperbolas? We've seen this before. So it's something to look out for. So if they said, what's the domain of the function I'm going to have g of x this time? Doesn't really matter. Oh, I'm doing it too low. Let's go back up here with this one. G of x equals 5 over 2x plus 1. Wow, changed it so dramatically. The domain for this, x can be almost any number except for 1. So my domain, I can say x is an element of the real number system, but 2x plus 1 is not allowed to equal 0, is it? So if I simplify that, 2x is not allowed to equal -1. oh, x is not allowed to equal -1/2. So you could then rewrite your domain, and if I want to do it really nice, x such that x is an element of the real number system, x is not equal to -1/2. There are different ways of writing the same thing. I don't know, for me that makes the most sense because it's really obvious what I'm doing there. Why can't it equal -1/2? Because then I divide by 0. Ones which you probably won't get yet, but we will get eventually. Logarithmic functions. We looked at logarithms at the end of year 10. What does my log graph look like? Anyone remember what it looks like? Yeah, it's a little bit like a banana. It's got an asymptote at x equals 0, doesn't it? If it's got an asymptote at x equals 0, it's because logarithms are only defined for the log of a positive number. I've got to have a positive number there. So that's another thing we have to consider. That diagram's a little bit out of place there, but I'll snip it and move it. Maybe. No, it's not going to let me do it. Oh. They're the three main ones that we'll deal with. There may be other ones later on, but they're really the three that you're going to look for in this course. It could be that just the question states a function is only defined for certain values. If it does that, if it just says in the question it's only defined for certain values, that could be a restriction, so you need to read your question carefully. Or it could be the context of a problem. I'm finding the distance, the length of a hypotenuse of a right-angled triangle. Does a negative value make sense? I could be talking about the position of a ball that's been launched by a golfer and they've hit it off the ground. Would time being negative make sense then? No, because the function's only defining it for once the ball's hit. So for time greater than or equal to 0. So it could be the context of a question that does that. Last little bit for you guys to do. We've got 5 minutes left. There are a few questions. Oh, what am I doing giving away the answers there? I didn't erase them all. Look at that. That's good. There are 6 little functions there for you to consider. Domain, D, the set of values that can go into it. R, the range, the set of values that you can get out of the function. Have a go and see if you can find the domain and range of those 6 functions there for me, please.
Make sure you use your function notation that we studied the